You've probably heard the sci-fi idea. When two galaxies collide, gravity pulls them together until they merge an unstoppable cosmic road that never ends. But what if there's an invisible break? What if, on the largest scales, the universe doesn't just resist motion, it can actively stall galaxy mergers before their light even has time to reach us from the far side? Tonight's open loop is this. Can dark energy create a horizon beyond which gravity can't complete its job? The surprising twist is that this question isn't only about far future fantasy, it's about an era already unfolding. Modern surveys show that the universe's expansion is accelerating, not slowing down. That acceleration reshapes how far gravity can influence cosmic neighbors. When two galaxies are relatively close, their mutual pull wins. But the moment their separation becomes too large, expansion takes over, and the merger may never finish. The phrase "beyond lightspeed reach" isn't saying galaxies move faster than light locally. It's describing a boundary in the cosmic web, a region so far away that by the time information and light travel, the geometry and expansion have already changed the outcome. To understand the before state, picture the early universe where everything was denser and expansion was decelerating. Gravity was a dominant force on large scales, so the cosmic expansion clock slowed as the universe aged. Galaxies clumped, clusters formed, filaments threaded the sky. In that backdrop, a natural expectation emerged. If gravity can pull, it should eventually pull distant partners into a single system. Even when mergers were slow, nothing fundamental seemed to forbid completion. Then came the late universe evidence. Type Ia supernovae revealed that the expansion rate is increasing. Cosmic microwave background measurements and large-scale structure reinforced the story. Something like a smooth, pervasive energy, dark energy, acts against gravity, causing the universe to expand faster over time. Now, the deep dive. Imagine two dancers on a dance floor that's stretching. If the floor stretches gently, the dancers can still hold hands and move together because their attraction keeps shrinking the separation. But if the stretching is strong enough, the dancers' hand-holding rhythm fails. They may lean toward each other at first, but the floor widens the gap faster than they can close it. In cosmology, that stretching is the Hubble expansion. Dark energy behaves like a uniform pressure that increases the expansion rate rather than letting it fade. The result is not that galaxies suddenly repel each other, it's that, beyond a certain scale, the pull that would bind them is overwhelmed by the metric's tendency to separate commoving distances. Here's where the horizon idea enters. There's a maximum distance from which signals can reach us in the future, the observable universe's effective boundary. With accelerated expansion, that boundary becomes tighter. For merging galaxies, it works like this. Their gravitational interaction must be strong enough, not only to overcome initial separation, but also to do so faster than the background expansion keeps increasing the distance. As dark energy dominates, the universe approaches a state where the expansion resembles an exponential growth. In an exponential universe, separation can grow exponentially with time, while gravitational binding, already weak at vast distances, doesn't scale fast enough to reconnect widely separated systems. So some pairs that might seem destined to merge in a decelerating cosmos never reach the late stage. They drift apart, become gravitationally irrelevant to each other, and effectively live on opposite sides of a cosmic divide. The story of discovery is a convergence. Observers mapped galaxy clustering, watched the cosmic web's growth, and compared it to models where gravity competes with expansion. If gravity alone sculpted structure, distant regions would keep knitting together more efficiently as time passed. Instead, the data show a slowing of structure growth. The universe forms big structures earlier, then the formation rate declines because dark energy prevents new large-scale collapses. At the same time, redshift surveys reveal that galaxies at great separations are increasingly out of causal contact in practice. Their mutual histories become disconnected as the horizon shrinks. Astronomers use simulations that embed dark energy into the expanding spacetime, then track trajectories under both gravity and expansion. The key result is a stall. Merger completion becomes unlikely beyond a scale that depends on dark energy strength and the mass of the galaxies involved. The phrase dark energy horizon captures this. A boundary not of physical speed limits between local objects, but of whether gravitational interactions can finish their work before expansion redefines the stage. What does this mean in the broader picture? It changes how we think about the universe's fate and the meaning of near and far. If there's a horizon for merger prospects, then the cosmic architecture is more of a snapshot than a continuously assembling mosaic. Superclusters that were forming may do most of their binding earlier. Later times produce fewer new massive unions because the expansion won't allow distant candidates to converge. This affects predictions for the population of massive galaxies, the growth of galaxy groups, and the environment where black holes feed and evolve. It also reframes our interpretation of large-scale surveys. The pattern of clustering isn't only an imprint of initial conditions, it's an imprint of dark energy actively suppressing growth. Even in a human scale, the implications are profound. Dark energy is the dominant energy component of the universe, yet it behaves almost like a property of space-time itself. If it can define horizons that prevent mergers, then it isn't merely a background term in equations. It's a mechanism shaping what combinations of matter become possible. That challenges intuition built from ordinary gravity in a non-accelerating world. And it sharpens a central question for physics. What is dark energy really? A cosmological constant, a new field, or something else that emerges from deeper theory? Each option predicts different behaviors for the horizon and for how structure grows, meaning that future observations could either tighten the stall or reveal a twist where gravity regains some leverage. So we come back to the hook. Dark energy doesn't stop galaxies from attracting each other in general. It stops the merger story from completing beyond a certain reach. As acceleration dominates, some would-be partners drift apart, and the universe's effective horizon determines which gravitational tails can have an ending. The beyond light speed reach isn't a violation of relativity, it's a boundary of causal opportunity in an expanding cosmos, where the geometry changes faster than binding can overcome it. The most unsettling part is that the universe may be writing its largest patterns early, then turning down the volume on further assembly. If you want more cosmic mechanisms that sound like science fiction but are grounded in data, subscribe for the next one.